Salam, peace be upon you. My name is Muhammad Laiq Siddiqui, the father of Holophase. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them the three dimensions show themselves at once: time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and the motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we focus on one essential component of the epistemic firewall. In this part 10, we cover the subtle but vital distinction between conventional constraints and canonical constraints. This is the filter that separates the invariant structure of reality from the human linguistic and mathematical choices we use to describe it. The skill you will gain is the ability to audit any scientific rule and ask, is this feature of the rule a fact about the world, or is it an artifact of my descriptive dialect? Our core question is, which parts of our rule language are human choices and which parts are invariants? This is a profound question of epistemic hygiene. In our journey from raw phi to sentences, grammar, and empirical laws, we make countless choices. How to label coordinates, how to calibrate instruments, what mathematical functions to use, what gauge or basis to pick. These choices create a descriptive layer on top of the raw phi patterns. The firewall must have a mechanism to peel back this layer, to ensure we are not mistaking our own convenient fiction for a law of nature. This mechanism classifies constraints into two categories: conventional and canonical. The core concept is this: conventional constraints are rules that arise from our choices of representation. They include coordinate choices, Cartesian, polar, spherical; gauge choices in electromagnetism and gravity; notation choices; discretization methods for computation; and even the choice of units, meters versus feet, seconds versus hours. These are not wrong. They are useful, often necessary, tools for description and calculation. But they are not features of phi itself. They are features of our map, not the territory. Canonical constraints are invariants that survive permitted rewrites. They are the rules that remain unchanged when you change your representation, provided the new representation is allowed, meaning it is a valid, consistent alternative way to describe the same phi patterns. A canonical constraint is a feature of the territory itself. It is what all accurate maps, regardless of their projection or language, must agree on. Let me state the audio equation that defines a canonical constraint. We say, a law is canonical if it remains unchanged under allowed transformations of representation. In symbols, we can write, if g of phi is a constraint and t is an allowed transformation, then g of phi is equal to g of phi t of phi. That is, the form of the constraint g, or the fact that it is satisfied, holds true even after we apply a transformation t to our description of phi. The transform constraint g of pi is essentially the same rule, just expressed in a new dialect. If it changes fundamentally, then g was not canonical. It was tied to the old dialect. Now, why is this distinction necessary? The failure mode it prevents is reifying conventions, mistaking a useful human choice for a deep truth about the universe. This error leads to pointless debates, artificial puzzles, and blocked progress. For centuries, philosophers debated whether space was absolute or whether time flowed uniformly. Debates often entangled with conventional choices of reference frame. The firewall, by forcing us to identify canonical invariants, cuts through such confusion. It ensures that the rules we fight over and build upon are actually about reality, not about our descriptive preferences. To understand this, consider an analogy from a familiar Afghan setting: giving directions. Imagine you are in the ancient city of Herat, inside the Great Friday Mosque. You ask a local for directions to the citadel. He might say, "Walk 50 paces toward the setting sun, then turn left at the old mulberry tree and walk 30 paces." This is a rule expressed in a particular convention. The convention uses paces as units, celestial markers, the setting sun, and local landmarks, the mulberry tree. Now, a second local might give directions in a different convention. Go 40 meters on a bearing of 250 degrees magnetic, then turn 90 degrees east and proceed 25 meters. A third, using a modern smartphone, says, go from coordinates 34.343 degrees north, 62.199 degrees east, to 34.345 degrees north, 62.203 degrees east. All three sets of directions can lead you to the same citadel. The conventional parts are the use of paces versus meters, the reference to the setting sun versus magnetic north versus GPS coordinates, the use of the mulberry tree as a waypoint. These are human choices, tied to tools, culture, and context. The canonical invariant is the geometric relationship between the starting point, the mosque, and the ending point, the citadel. This relationship, the vector displacement, the fact that the path involves a specific turn, is what survives translation between all these descriptive dialects. If a rule, like you must use a mulberry tree as a waypoint, only works in one set of directions, it is exposed as a convention, not a canonical feature of Herat's geography. The firewall of good navigation is the ability to extract the invariant geometric core from any set of conventional instructions. In Holophase, the citadel is a phi pattern we wish to describe. The different sets of directions are different mathematical representations or coordinate systems. The canonical constraints are the relationships between phi and its derivatives, the omega of k or v relations, that hold true no matter which mathematically allowed coordinate system or gauge we choose to write them in. Now, what is the formal meaning in holophase terms? We describe reality using phi of xt, but the labels x and t, the coordinates, are themselves conventions. We could relabel them. We could apply a smooth invertible transformation to get new coordinates. X prime equals f of xt, t prime equals g of xt. This is a change of representation. The underlying phi field is the same reality, but its functional form phi prime of x prime t prime looks different. A canonical constraint is a condition on phi and its derivatives that, when translated into the new coordinates, still has the same physical meaning. It still describes the same restriction on possible phi patterns. The triunity is crucial here. Representation changes can reshuffle how omega, k, and v are written. For example, changing from a stationary coordinate system to a moving one mixes space and time coordinates. What looked like a purely spatial pattern, a specific k, in one frame, may appear as a mix of omega and k in a moving frame. What looked like a propagation speed v may change. However, true canonical constraints survive the reshuffle. The underlying relationship between the rhythms, structures, and motions, the essential phi pattern, remains invariant. The constraint might look different algebraically, but it forbids and permits the same set of possible phi sentences. Let's connect this to energy as tally. Energy is a derived accounting from omega kV relations. Therefore, a key test emerges. If the numerical value or form of energy changes when you change your representation in a way that should not affect physics, then you measure the convention, not a canonical law. For instance, in Newtonian physics, the kinetic energy of an object depends on your frame of reference. In one frame, it's half mv squared. In another moving frame, it's a different number. This tells us that the specific numerical value of kinetic energy is not canonical. It is conventional, tied to the choice of reference frame. However, the law of energy conservation, or the form of the Lagrangian from which energy is derived, can be canonical. It holds its form across certain frame changes. This distinction is at the heart of theoretical physics. The firewall demands we be ruthlessly clear about it. Think of it like accounting for a business that operates in both Afghanis and US dollars. The conventional part is the specific number in a specific currency. A profit of 100,000 Afghanis is a different number than a profit of $1,200. But they can represent the same underlying economic reality at a given exchange rate. The canonical invariant might be the profit margin percentage or the real purchasing power, which should be consistent when calculated correctly through the exchange rate. If your assessment of whether the business is profitable flips depending on whether you use Afghanis or dollars, you have made a conventional error. You've confused the currency label for the economic substance. The canonical firewall insists on invariants like purchasing power. The operational interpretation of this firewall function is the practice of invariance checking, or covariance analysis. When a theorist proposes a new constraint G, a standard part of the validation is to test its behavior under allowed transformations. These are defined by the theory's own principles. In special relativity, allowed transformations are Lorentz transformations. In general relativity, there are smooth coordinate transformations. In gauge theories, there are local gauge transformations. The procedure is: write the constraint G in a given representation, a choice of coordinates, gauge, etc. Apply an allowed transformation T to all quantities in G. Derive what the constraint looks like in the new representation. Call it G prime. Check. Does G prime have the same physical content as G? Does it restrict phi patterns in the same way? If yes, G is a candidate canonical constraint. If no, G is representation dependent. The firewall role is to block the epistemic failure of gauge dogmatism or coordinate literalism, the insistence that a particular mathematical representation is physically real. It reminds us that the map is not the territory. Only the invariants are the territory. Let's state clearly what assumptions are allowed and forbidden. Allowed. You may choose any convenient, consistent representation, coordinates, gauge, units, to perform calculations and communicate results. You may use conventional constraints as helpful scaffolding. Forbidden. You may not claim that a feature of your chosen representation is a fundamental law of physics if it disappears or changes under an allowed transformation. You may not build physical interpretation upon conventional elements without demonstrating that an invariant core lies beneath them. What happens when the check fails? When a proposed constraint is found to be representation dependent, the license consequence is downgrade to representation dependent claim, restrict its scope to that specific representation, and require an invariance proof to be reconsidered. The claim cannot be promoted to a canonical law. It is understood as a useful formula within a specific dialect, not as a statement about phi itself. Now we must state the explicit prediction and falsification for canonical constraints. Prediction. A canonical constraint yields the same omega kV relations under multiple representations. That is, if you reconstruct a phi sentence from data and check the constraint in one coordinate system, and then you transform both the data and the constraint to a different, allowed coordinate system, the reconstructed omega, k, and v values will obey the transformed constraint in a way that describes the same physical pattern. The predicted relationship between the echoes is invariant. Falsification of canonical status. If the constraint holds only in one dialect, one specific gauge, one coordinate basis, one notational scheme, and breaks or changes meaning in another allowed representation, then it is not canonical. The falsifying condition is failure of invariance under allowed transformations. The rule is exposed as being glued to our language, not to phi. A classic example is the concept of simultaneity in pre-relativity physics. People believed simultaneity was a canonical invariant, that if two events were simultaneous for one observer, they were simultaneous for all. This was a proposed constraint on the relationship between time, omega, and space, k. Special relativity showed this constraint was not invariant under Lorentz transformations, the allowed transformations between inertial frames. Therefore, absolute simultaneity was falsified as a canonical constraint. It was a convention tied to a specific class of reference frames, those at rest relative to the ether or to a preferred state of motion. The canonical invariant that replaced it was the space-time interval. Now let's explore an Afghanistan-inspired analogy to cement the difference and show the danger of confusing the two. Consider the rule for determining the start of Ramadan based on the lunar calendar. There are different conventions. One convention is the local sighting of the crescent moon with the naked eye. Another convention is astronomical calculation, predicting the new moon. A third might be following the declaration from Saudi Arabia. These are different representational systems for mapping the celestial mechanics of the moon, earth, sun system, the underlying phi pattern, to a social religious date. Now, a conventional constraint would be the month begins only upon a verified sighting by two just witnesses in Kabul. This rule is tied to a specific method, sighting, and location, Kabul. It is useful and has deep cultural resonance, but it is not an invariant of the celestial mechanics. It can lead to different communities starting Ramadan on different days due to clouds or differing witness testimonies. Differences arising from the convention, not the astronomy. A canonical invariant underlying this is the astronomical new moon, the precise geometric alignment. This is an objective fact about the positions of the bodies, calculable and invariant no matter which observation method you use, sighting, calculation, or following another country's announcement, which is itself based on some method. The firewall insight is to recognize that debates about the true start of Ramadan often conflate arguments about canonical invariants, the astronomical moment, with arguments about valid and meaningful conventions, citing versus calculation. The epistemic firewall in this context would demand clarity. Are we arguing about the invariant celestial geometry, or are we arguing about the chosen human protocol for mapping that geometry onto a social practice? Both are important, but they are different. Mistaking a cherished convention for the canonical invariant leads to unnecessary conflict and confusion. In physics, the debates over the true nature of the gravitational potential or the electromagnetic vector potential have often suffered from this conflation. These potentials are, in many respects, conventional. Their specific values can be changed by a gauge transformation without altering the canonical invariants, the electric and magnetic fields, which are related to derivatives of the potentials, and the forces they produce. Now we must state the mandatory episode 11 axioms in this refined context. Rules do not become real by elegance, consensus, or tradition. They earn a license only by surviving falsification, variation, independence, and scope discipline. For a rule to be canonical, it must survive the falsification attempt of changing representation. It must show variation in its descriptive form while retaining its core. Independence is demonstrated when different researchers using different notational or calculational conventions converge on the same invariant. Scope discipline for a canonical rule is about the domain of allowed transformations under which it remains invariant, its gauge group or symmetry group. And when a rule fails, we do not believe harder. We tighten, downgrade, or retire its license. When a rule fails the invariance test, we downgrade its license from canonical to conventional specific, tightening its scope to a particular representational scheme. The skill you gain from this part is invariant extraction. You learn to look at any complex equation or scientific statement and ask, what here changes if I change my descriptive language, and what stays the same? What are the allowed transformations in this theory? Does this claim survive them? This skill is the mark of a sophisticated theorist and a critical consumer of science. It allows you to see past the often arbitrary surface of equations to the invariant structure they attempt to describe. This has immense practical importance. In computational physics, you must discretize continuous equations. The choice of discretization, finite difference, finite elements, spectral methods, is a convention. The canonical constraint is the continuous equation itself. A good code is one whose results converge to the invariant solution, regardless of the conventional discretization choice, within limits. The firewall reminds us to check for this convergence. Finally, let's summarize the epistemic function of this part. We have defined conventional constraints as rules arising from our choices of representation: coordinates, gauge, notation. Canonical constraints are invariants that survive permitted rewrites of that representation. The audio equation is: a law is canonical if it remains unchanged under allowed transformations. The triunity test: true constraints survive the reshuffling of omega, k, and v descriptions that occurs when you change representations. Energy as a tally must be based on canonical invariants. If the tally changes meaning under allowed transformations, it's measuring a convention. The explicit prediction is invariance of omega k vive relations across representations. The explicit falsification condition is breakdown of the constraint under an allowed transformation, exposing it as representation dependent. The license consequence is downgrade to a representation-dependent claim, with a restricted scope and a requirement for an invariance proof for reconsideration. This strengthens the firewall by adding a final layer of purification. It ensures that the laws we archive and rely upon are not contaminated by the arbitrary choices we made during their discovery and formulation. It drives us toward the invariant core, the true grammar of phi that is independent of the human observer's linguistic or mathematical accent. This is the ultimate goal of physics: to find the canonical constraints, the symphonies of omega, k, and v that play the same tune in every possible hall of mirrors. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. Carry the discipline of invariant extraction with you. It is the scalpel that separates human invention from natural law. In every equation, in every model, hunt for the canonical core. Now we bridge to the final consideration for our firewall. Even after we find the canonical empirical rule, a question remains about its strength and limits. Now, even canonical rules have a weakness. How strong is the rule, and where does it crack? This leads us to the final component: rule strength and failure modes. Salam, and peace be upon you.